The sun is to the right. South. That was a nice country. Far away from.
They want to enjoy very somewhere in that
You can go to, yeah, just to the south. You can ski. You can ski on volcanoes.
It's so active.
It's dormant, right? Well,
no, it's active volcano. It's and
from time to time you have lavas.
there are big warning signs when you ski where you should not be if there is volcanic.
Yes.
Yeah, so
No, surface. Just to insulate it is like.
Can you ski?
No,
What you can
teaching.
ski?
I see.
I think that
Is in this yes, local days. Local days also.
They implemented third parts of ski left, right?
is it natural?
In Japan, you can ski as well.
I think that's very special what this is. If you have met.
You get snowflake?
Yes. So.
Just look at it.
Okay. So, dear PCS members and friends, welcome back to our seminars. And our scientific host is still Professor Sergei Flach, who will introduce our next speaker.
Yeah, thank you. And this is part 2 of our New Zealand workshop, one-day workshop. The second speaker today is Professor Joachim Brand. Let me shortly introduce Joachim. He also did apparently his undergrad and studies in Heidelberg, so there's clearly some correlation. And then he also went for a postdoc, for a research associate to the University of Washington, Seattle. And then he also went as a researcher to the Max Planck Institute for the Physics of Complex Systems, where again we met for the first time, I guess.
Yes.
And then he moved on to New Zealand, to Massey University as a senior lecturer in 2006. And then he moved there through the ranks, and where he's now full professor and member of the New Zealand Institute for Advanced Study. He has lots of publications, I think more than 80 probably. And he has lots of distinctions. In particular, what I want also to mention is currently the deputy director of a big New Zealand-wide research activity called the Don Walsh Center for Photonics and Quantum Technologies. And he was also recently the president of the New Zealand Institute of Physics, NZIP, which is a rotating position, if I understand correctly, for 2 or 3 years. Right, and today he will talk about odd frequency superfluidity from a particle number conserving perspective. So let's welcome Joachim.
Well, thank you very much, Sergei, for the kind introduction and also, of course, for the invitation and the opportunity to be here and give a talk. It's a great pleasure. It's actually my second visit to this institute. First one was a virtual visit during COVID times. But it's really good to be here in person and actually, yeah, be here on the ground. Right, so this is a column. So the talk, I cheated a little bit with the title. So you will get a lengthy introduction on different topics. And then we will come to the main topic of odd frequency superfluidity. And this is a collaboration with a gentleman you see here, where Kadin, Uli, and Michele. They're all researchers at a different university in New Zealand, Victoria University of Wellington. And also Jörg Schmaljang from Karlsruhe joined this collaboration, but I will introduce members of my research group at Mass University later. Sergei already mentioned the Dot Wall Center, which is a research center that in New Zealand, and center in New Zealand means it's not a center really, it's delocalized. It's more a research collaboration between different universities, which you see here on the map. We're here at Mass University at the northernmost node of this research center. And it's actually not exactly true what Sergei said. I'm no longer the deputy director, but I was until very recently. So I'll pass this on. And so the Dot Wall Center is a center for photonic and quantum technologies. So one of its, one of the areas that works in is ultra-cold atoms, quantum gases. So this is mostly where my own interest is, and then there's a lot of atoms, including biophotonics. Right, so here's an overview of my talk. So I will talk about, so as a sort of lengthy introduction as a first part, it's about projector quantum Monte Carlo in Fock space, and that is partly motivation for why I'm interested in particle number conserving perspective on odd frequency superfluidity, because that is how you would approach it from the computation point of view. But I will explain what that is and give you a few examples here of how it works. I thought that might be interesting because it's more of a tool that other people might be interested in using. Right, so here is a recent photo from a recent group hike, and you see there are members of my group. So Mattia and Satyanand are PhD students in my group. Actually, Mattia did a lot of coding, really good work on this quantum Monte Carlo package that we're publishing. Alex is a postdoc in my group. Now, you see Elke, and there's an apparent correlation as in Sergei's introduction. Elke is my wife, and we moved from place to place. So we now, in this topic, we have a strong collaboration with Elke, and Jamie is a student supervised by Elke mainly, but she also works on the FCI-QMC topic. And here is a picture from actually 8 years ago from a sabbatical in Stuttgart. So these were people who were early on involved in our work in FCI-QMC, in particular Ali Alawi. He developed the method in the context of electronic structure theory, and then we're now using it for mostly other problems related to ultra-cold atoms. Right, so with quantum Monte Carlo, we want to solve a number of different problems. One of them is finding ground and excited states. That's actually the starting point, probably, time-independent Schrödinger equation. But there are algorithms for all these other problems. Let's say finite temperature physics, sampling the density matrix, solving the block equation, driven dissipative dynamics, and also just real-time quantum dynamics, which is something that we're currently working on. And the references that you see here, they're all papers that more introductory or proof of principle papers that show that you can do all of this with extensions of FCI-QMC. I will introduce what that is. Before I do that, here's the advertisement bit. So we have developed a open source package for FCI-QMC, which is available. It's written in the language Julia. And the idea was, because FCI-QMC did exist, but it was all used by quantum mechanics, so we wanted to have something that not only deals with spin-half fermions, essentially, right? So, and work with bosons and problems that are, in sort of a little bit more general. Right. Right. So word on Julia. I don't know. Can I have a show of hands? Who is using? Is there other people using Julia in here? Okay, already quite a few. So probably I don't have to tell you what Julia is or how good it is. So we love it. This diagram is supposed to show that it is fast. So this is a time comparison for execution of some micro benchmarks in reference to C. So Julia is, pretty close here. It's a high-level language, but it sort of compares with the compiled languages, which is really nice, but is as easy to use. Or the idea is, it's comfortable as, programming in MATLAB or Python maybe, which are just much slower languages. Right. So this was the reason why we choose to implement a quantum Monte Carlo code in Julia. So we can fast code, but it's also really nice to use. And you can plot the results right in the same language in which you write the the number crunching routines. So why full configuration interaction quantum Monte Carlo? It is a flavor of projector quantum Monte Carlo. So primarily to solve the time-independent Schrödinger equation, find the ground state, energy, and sampled wave function as well. And of course, projector quantum Monte Carlo is not, the idea is not new. It's been around for quite a while. There are a number of different flavors. So this flavor here was, started, first publication is 2009. What I find attractive to it, from it, is that it's a really natural, or the most natural and direct extension of exact diagonalization that you can find. So you can code up a problem that you know how to solve as a exact diagonalization problem, and then you can say, okay, now it becomes too big for actually solving it on a computer as exact diagonalization. Now you can Monte Carlo it, and then you can extend it to much larger problems. Right. So, this is maybe a little bit boring about the developments. So there are some methodological developments that were done. We had some modest contributions here, improving population control and analyzing population control bias in this method. So what is it about? How does it work? So you start with representing a Hamiltonian in a basis of Fock states, right? So this is what you would do for exact diagonalization as well. Let's, for example, take a Bose-Hubbard Hamiltonian, which looks like this. If you represent it in this basis of Fock states, it has a sparsity pattern that looks like this. So this is the form matrix for, a fairly small system, but as you know, the Hilbert space scales exponentially with system size and particle number. This becomes very quickly so large that you can't store the matrix anymore, or even storing the vectors, and that is when Monte Carlo comes into play.
But by Fock states, you mean eigenstates of some non-interact or some reference Hamiltonian?
So with Fock states, I mean sort of products, symmetrized products of single particle states. So you take some single particle operator, Hamiltonian, non-interacting, and then they are the non-interacting many of the eigenstates. And they're in particular the eigenstates of particle number. So the principle is that we write an iteration equation with a transition operator T here that is applied again and again to the same vector. So this realizes the power method, or you can also understand it as a discretized imaginary evolution, right? So if you do this iteration exactly as a matrix vector multiplication, so T is a matrix now, H is our Hamiltonian realized as a matrix, it will eventually converge to the exact solution of the right coefficient vector, and then the scalar shift here, this is a scalar parameter that is updated at every time step with an equation that I didn't write for you, but it's updated in such a way that the norm doesn't change, becomes stable. Then this will become an estimator for the energy, and the coefficient vector will be the exact ground state.
Why it cannot stuck somewhere far from ground state?
Exponential.
If delta tau is small enough, you can prove that it will just find the ground state, because it is well, it's just imaginary time evolution, right? So you have an exponential. For each eigenstate, you have an exponential time evolution, and the ground state is the one that decays more slowly.
But you also need to assume that the state that you begin with has a non-zero overlap with ground state.
Yes. Okay. Thank you. Yes, of course. You should not be in an orthogonal subspace to it. So the ground state, the initial state, needs to have an overlap. Now, because eventually we will do things stochastically, it's not so important that the initial state does not have an overlap. But of course, if it is in a sector with a different symmetry, you will converge to the ground state of that sector, which is sometimes actually even useful, because then we use that, for example, for momentum eigenstates. If in translationally invariant systems, we can get the ground state at given total momentum. Right, yeah, thank you for the question. So now, how do we do this in Monte Carlo way? So this is how FCI-QMC now differs. So first of all, if you just did it in the way as it was on the previous slide, it would be a fairly inefficient way to find the ground state. However, it's good for the Monte Carlo procedure. So what we do there is, it's really just a multiplying a vector with a matrix, and then there's a stochastic compression acting here. So what we do, each matrix element is multiplied by this vector, but now the vector is stochastically sampled. So we do the diagonal element every time, but the off-diagonal matrix elements is chosen stochastically, which one is actually going to be multiplied. So they will all be summed up into the final vector, and then there's another step of a vector compression that is done stochastically, and the whole thing is designed in such a way, the stochastic process is designed in such a way that by expectation value, you actually do the correct matrix vector multiplication. Right? So this is one aspect, and the other aspect is that because you don't do all of the off-diagonal matrix elements, and because you compress this vector, you don't need to store the whole vector. You only store the non-zero elements.
So with the specific Hamiltonian,
Yeah.
you change your sampling so that the answer should be more correct.
No, actually, the beauty of this is that this is very general. You can basically apply this to any matrix. It will be very inefficient if your matrix is not sparse, so it works best for sparse matrices. But yeah, so the beauty is here, this is really very generic. So any problem that you can express as the ground state of a Hermitian matrix eigenvalue problem. Actually, it doesn't even have to be Hermitian. We do this for non-Hermitian matrices as well. The algorithm doesn't need to know about the details of the actual problem. Sometimes you can make it more efficient by doing something that we call importance sampling. So it's the idea of importance sampling is the same as in other Monte Carlo methods, but here we formulate this as a as a similarity transformation on the vector. On the matrix. So that can make it more efficient. But otherwise, the beauty is you just define the Hamiltonian essentially in the code, and then you put it into this algorithm and you crank the handle, and you get out the result. Yes.
So starting initial Cn itself is already random vector. Starting initial.
Yes. So in fact, yes, that's what you would do in linear algebra. You would use a random vector in the hope that that will have some overlap with the ground state. Right now, here we don't actually do that. We use just a vector which we assume is somewhere close to the ground state. It's sufficient if we have just often we start just with a single configuration, a vector that just has one element basically, with a single configuration, which is the one that has the lowest diagonal matrix element, for example, and then time evolved from there.
Then select the column of the element, so randomly, stochastically.
Yes. So the off-diagonal elements of this column, they're sampled stochastically. Yes. And there are and right now we do this. We need to know how many non-zeros there are, and then we sample them in a uniform way. But yes, you can make it slightly more efficient if you have some information about which ones are the larger ones and which ones are the smaller ones. Yeah. So in quantum chemistry, this is done as sometimes, and it's called heat mass sampling. So that makes it more efficient. So we've mostly been working with model Hamiltonians with Hubbard models, where actually it's not so important because the values of the non-zero matrix elements are usually about the same. Yeah, so they don't vary very much in magnitude. But yes, there are efficiencies to be gained if you know more about the detailed structure.
Are the statements from the previous slide still active, that this is leading you to the exact ground state if you're on the right symmetry sector?
Yes, it will give you an answer that fluctuates around the ground state. Yes, so by expectation value, this was still the correct. So I didn't include those on the slide, so that is good. Good question. So you'll have a transient. So you get a time series, you iterate this, right, for many time steps. You get a transient, and after this transient, the coefficients will fluctuate around the correct coefficients, and the shift will fluctuate around the correct energy. And then what you do is after this transient, you take averages.
And what about these amplitudes of these fluctuations? What do they depend on?
Well, they will depend on, first of all, if you have inefficient sampling, there will be, may depend on the details of the Hamiltonian. The other control parameter that we have is the norm, right? So this doesn't have to be normalized to work. And the way we discretize it is we discretize basically just by integer values. So if we want to do a very calculation that has very little noise, we take a large norm of this vector, and then we have to do more work because the discretized steps, we will do more of those. And then, and then this decreases the noise in the result. And will eventually also sample,
Sorry,
more efficient.
slide,
Yes.
this S10 that you had,
Yes.
is this one you obtain from the iteration method, or is it, how do you obtain that SN?
Yeah, there's a second equation that I didn't write, which updates the shift, this value Sn at each time step,
Okay.
and is updated in such a way as to control the norm, right? Because if we do, this is a linear equation. If the shift is constant, this would be a linear equation discretized linear differential equation would either grow exponentially or decrease exponentially. Right. So there's a second equation that we use to update the shift depending on the change in norm, and it controls the shift in such a way that it reaches a certain target value of the norm that we set frequently as a parameter. It's actually quite neat. It realizes a damped harmonic oscillator, which also explains why you have transients.
You said that it's related to the norm?
Yes.
I thought it was related to the eigenvalue. No?
Well, so what we can always measure after we've done one step is how the norm has changed of this vector, right? Because it, as I said, it could either grow exponentially or decrease exponentially, right? So if we change this value, the shift, we can control whether it grows more or less. So it's updated in such a way that eventually it actually converges, that the norm converges to a predefined value. And if it does that, then, and we reach a stationary limit, then we're guaranteed that the fixed point actually satisfies these equations. And you can show that it has an instability if delta tau is too large, right? And the largest, if delta tau is small, then it's all fine. It converges it's a stable fixed point. And delta tau has to be smaller than the inverse spectral range of the Hamiltonian, right? So there is a problem if you want to scale up your Hamiltonian to make a really large system. You may have to take smaller and smaller time steps. Otherwise, there is no time step error. Some Monte Carlo methods have a time step error where you have to extrapolate to a small time step. This one doesn't have that. It has an instability. Right. So this basically explains in theory how the method works. And now I want to show you in examples where we have used that method and where we got some really nice results. So one very recent project that we're, yes, in the back. Sorry, I didn't hear the second part of your question. Can we target the middle of the spectrum? Okay.
Excited states.
Well, I will show you excited states, but these are low-lying excited states. Maybe, but I would have to. So we haven't done it, and I would have to think a little bit about whether it's possible to do that or not. But happy to talk about that later if you're interested. So in this particular problem, we were interested in actually not only the ground state, but we were interested in low-lying excited states. So the Fröhlich Polaron problem is a very old famous problem. Initially Landau and Pekka thought about this, and then it became one of the most studied problems in quantum many-body theory, maybe to some degree. So the general idea is you have the motion of a single electron in a polarizable medium. So this could be the ions in the lattice, but we're working in a limit where the lattice disappears and it just becomes a polarizable medium. And we're solving the Hamiltonian in this form, where P is the total momentum, including the electron and the lattice vibration. So these are phonon modes, excitation, so creation and destruction operators of phonon modes. Specifically, we're working with the one-dimensional version here, so there's only one direction of phonon modes. So P minus the phonon momentum is the electron momentum. squared. This is just the energy of the phonons, which is assumed to be constant, optical phonon, and this term here describes the interaction between electrons and phonons. Now, interesting. So we in this formulation here, the Lilo-Pines formulation, we have only phonon modes to work with. But an interesting aspect is that the phonon number is not conserved. So even when we discretize the modes, as we've done here, and we are working with a finite number of phonon modes, we still have, in principle, an infinite Hilbert space because the number of phonons is not controlled. Now, we're cutting this off practically, just because the number we use to store the number of phonons we have is 8 bits. So we have 256 to the power of the number of phonon modes we use, which for the largest examples of the calculations we did was 73. So this gives you a ridiculously large Hilbert space, right? So previously I talked about a matrix. This is the linear dimension of the matrix that we're actually considering here. Now, most of the works on Polaron traditionally have looked at the energy of the electron, being dressed by this phonon dressing cloud, and as a function of momentum, it has this type of energy dispersion, and there is a continuum, a scattering continuum of phonon modes above that. Which, of course, when we discretize it, will become a discretized continuum. But there was, so our collaborators, David Metroskas and Robert Seiringer, they realized a few years ago that there is, they're mathematicians, I should say, or mathematical physicists. So they proved that at weak coupling strength, there are no bound excited states. And then they proved that for large coupling strength, there are infinitely many bound excited states here. And only very recently, my student dug in the literature and found that, in the Russian literature, actually quite a long time ago, Melnikov and Rashba already predicted that there would be excited bound states. So these are bound states where you can think of this as the electron has a dressing cloud and it binds additional phonons to it. Yeah? So these are excitations of the phononic dressing cloud. But yes, so this was basically not known when Metroskas and Seiringer did their work. Just recently found that out. But what they didn't know was at which value of the coupling strength do these bound states appear. Right, because there's only results for infinite coupling or weak coupling. So this is where we, So actually, I met Robert Seiringer a few years ago, and he asked me, "Can you calculate that numerically?" And I thought, let's have a look. Right, so that's where we employed the method for. So this is just a test calculating the ground state energy. So in red are our results from FCI-QMC, and green is a weak coupling expansion, right? Because again, this is a well-studied problem for weak coupling. You can analytically write a couple of terms in an expansion for small alpha, and purple is a strong coupling expansion. They nicely overlap here, and you see that FCI-QMC captures well into the strong coupling regime, the physics quite well. Right, so then now we look for excited states. And the way we calculate excited states is fairly straightforward. So we run multiple simulation replicas at the same time and orthogonalize them at each time step with the Gram-Schmidt procedure. Now, here I should mention the Monte Carlo sign problem. It doesn't occur for the ground state, but for these excited states, it occurs, it's unavailable, it's unavoidable. So there is a Monte Carlo sign problem, and the way it appears in FCIQMC is also actually quite interesting. It leads to wrong values for the shift for the energy estimator here if the norm of the vector is too small. And then there is a particular point, and that is, in practice, a phase transition above which the sign problem is mitigated or ameliorated by.
So basically, the idea here is that you found the ground state, and then you found the lowest end is the excited states that orthogonal with the ground state.
Yes. Yes, exactly. Exactly. And in practice, this is done by running both simulations at the same time, because we only get this, we get this fluctuating time series of states. Right, and we have to use a large enough norm, and that is it's a particular feature of FCIQMC. I think other projector Monte Carlo methods cannot do that, because walkers of positive and negative sign, they can annihilate, and if there's enough of them and they annihilate, then there's spontaneously break the symmetry of the sign, and you get a sign coherent solution, essentially. Right, so we can find these excited states as well without any additional approximation. Right, so the ground state is here. The different colors are for different values of alpha, and the excited state is here on top. Right, so and this is what the results look like. Now, as a function of coupling strength, the ground state energy has already been subtracted, so these are only excited state energies. We find one excited state exactly at 1 h per omega, which is the known boundary of the excitation continuum. So the excitation, the scattering continuum of excited states is here, is shaded, and we only see a few states there, and that is because of the discretization that we've applied to the system. But then we see that at some critical value of alpha, one of these states goes below this excitation continuum. So this is now the first bound excited state that we find there. And the dashed line is a prediction for infinite alpha, where we have an analytical result. Right, so the nice thing is that we find a threshold value for the bound state at an intermediate interaction strength. It's actually not very large, 1.75 roughly, 1.73. So this is why I was interested yesterday in the talk of people who do one-dimensional chains of molecules, and it would be interesting to see whether people can actually realize this one-dimensional model, and maybe even find these bound excited states experimentally. Right, I do have I'm seeing the time is progressing. Maybe I will not talk about this second example very much. It is a lattice problem, Bose-Hubbard model, but again, the story is FCIQMC actually works quite well to give us insight into strongly interacting physics here. This is for the, just very briefly, this is for the Mott-Hubbard, for the Mott insulated to superfluid transition. It gets that right, but that of course was known before. The work that we recently did was related to putting an impurity into this model as well, and getting some strongly correlated physics near this phase transition, quantum phase transition.
So how do I have to understand this? You mentioned that your Hilbert space dimension can be easily like 10 to the power 175 or something like that. So when you do these practical calculations, let's say for the particle, where is this? really you are not scanning 10 to the power 175 numbers on your computer, right? So can you explain maybe again how this disappears and you still get an exact, as you say?
Yes. That it is kind of amazing. I'm wondering whether I should go back to one of those slides.
Or let me ask you, so probably when you get the energy, maybe I can still understand it, yeah? So you are saying that you will in principle get the exact energy.
Yes.
But there's clearly something, you don't scan the entire Hilbert space, so to say, so.
Well, on average, we would scan the exact Hilbert space if we waited long enough, right? In principle, every element of Hilbert space is accessible and can be scanned. Now, here you see this is, well, we call it the norm of the vector, but we also call it colloquially the Walker number. This is also a limit on the maximum number of non-zero elements that we store. Right, so we increase that, and you see, this dimension of Hilbert space is ridiculous. And for the ground state, for example, we see larger error bars and then smaller error bars as we increase this number. Now, as I said, we did not put in a cutoff on our cutoff on the number of phonons in each mode is 256 or so. At these values of alpha, which actually are not written here, the average occupation is very small. 1, 2, 3, 5, less than 10. Yeah, so it's very rare that you would get an excitation where you would have an example where you have many phonons. But in principle, it is accessible.
So you could make it big, this number, right? What kind of parameter do you have to tune in the Fröhlich problem to have lots of phonons in the polaron?
Yeah, alpha.
Alpha.
I don't have, so alpha is this coupling strength. As you crank up alpha, the number of phonons grows. I don't have a plot here. We have calculated it somewhere. Elke, do you remember how large a number gets if we get to 4 or 4.5? It's still
number of focus we need was 10 to the 7. 10 to the 7 or 10 to the 8, something like that.
Oh, that's the number of walkers we used, yeah, but the number of phonons that are actually dressing, well, we had the number of phonons per mode. Ah, yeah, so that is in the paper. I can show you later. But again, it's between 1 and 2 or so, right? Average number of phonons, the phonon density per mode.
Probably still small.
It's still fairly small.
Yeah. And
so are there problems, are there systems or Hamiltonians where this method will not work very well? Probably they are.
Yes.
What distinguishes them?
Okay, so very famous problem would be two-dimensional Hubbard model with fermions at near half filling with some doping. And what distinguishes them is that, so here for this to work, the dimension of Hilbert space is immense, but if you were to plot okay, so actually I can do this. So the CNs are our coefficient, right? Let's put the amplitude over n and that's sort them in such a way that by decreasing magnitude, if you have a vector that has very large amplitudes here and then a tail of very small amplitudes, then SCI-QMC works quite well. But you can have strongly correlated problems where the amplitude is basically constant, right? If you really need the huge Hilbert space, then and in particular if you have a sign problem as well, then this does not work.
But then the 2D Hubbard at half filling or close to half filling, I thought can be work well with if you use some kind of incremental expansions. So essentially, so there are methods which work well when you have short enough correlations, which decay fast enough in some whatever real space in which you set up your POC states.
Well,
But this is not the case. So you don't need short correlations here. That's not the.
No. Essentially, we need this property here. That the majority of the weight of that vector in Hilbert space is carried by a small and fairly finite number of configurations.
Configurations means states.
POC states.
Yes.
Exactly.
So you have to be close enough to the true eigenstate, in a sense.
Yeah. Or you could say if you have a matrix that is sort of near diagonal, it doesn't really have to be near diagonal, but the number of configurations that actually matter then for the ground state has to be fairly well. A small number that have a very large weight. So this is what helps. Yeah.
And then if in this case, if you have the phase transition, then how can you capture the phase transition point, the critical point? Scale invariant, then basically.
Right. So we can, and demonstration is here. So here we do have a quantum phase transition in the Bose-Hubbard model. Now, in the Bose-Hubbard model, what you have is, this is a Mott insulating regime where U is large and J is small, right? So this gives an energy penalty if there are more than, if there are more than one boson at each lattice site. So in this regime, and we work at unit average filling, so the Mott insulator is filled, one boson is at each site. So here you have an extreme example, right? You have this Mott insulating state, and then all excitations are energetically forbidden. You can still access them, but the energy cost is fairly high, so you don't. Now, at the phase transition, that changes, and then you get into the superfluid regime. In the superfluid regime, you have a very different state, which is actually, it becomes really hard to converge FCI-QMC further you go into that superfluid regime, if you work in that basis.
So you have to change the basis.
Yeah, if you work in a momentum basis, then the superfluid state limit is trivial, and then the Mott insulating one gets hard. And that's the same with the Fermi-Hubbard model as well. Now, luckily for us, the phase transition is actually still quite okay. It's fine. It's just away from the phase transition where it becomes hard. Right. Okay. Any more questions on the FCI-QMC part? Because I'm going to switch to a slightly different topic. It's sort of motivated by my interest here in working with number-conserving methods. If you have a number-conserving Hamiltonian. All right. So yeah, maybe I can do that actually quickly, so we don't not here forever. Okay, so superfluidity is, in essence, for helium, these are bosonic atoms. So main thing is that these bosons condense, and you have a Bose condensate, which gives rise to the superfluid properties. Now, for superconductors, you have electrons pair up, and the Cooper pairs are bosonic, and again they condense and give rise to the superfluid superconducting properties. Now, in ultra-cold atoms, which is the field where most of my interest lies, you can actually measure these pair correlations directly, and I'm showing you results of a recent experiment here from Selim Joachim's group at the University of Heidelberg. So where they had, was it 12 atoms or something like that, fermionic atoms, in a optical dipole trap here with, in a tweezer and then squeezed to 2D harmonic confinement. And they have an imaging technique where they turn off their tweezer confinement. So the atoms fly out, they wait a little while, and then they take a measurement, and they have a quantum gas microscope where they can collect fluorescence from each of the atoms and detect actually the position of each of the atoms, and they even can separately detect spin up and spin down atoms. Right? So here you see one of these pictures. Blue and red are either spin up or spin down. And because this was done after some expansion, this gives you a momentum space picture in 2 dimensions. The dashed circle here is what would be the Fermi sphere, the non-interacting harmonic trap confinement. And if you see atoms, atom pairs spin up and spin down that are correlated near the Fermi surface by K and minus K, so that indicates the formation of Cooper pairs. And it's quantified a little bit more here, so you see that. So what they really measure is this correlation function, pair correlation function, or it's a part of the 2-particle density matrix, and measure one atom here and then see what is the probability to have an atom with the opposite spin on the other side. And you see these correlations nicely appear from left to right. It's increasing attractive coupling strength. So this is non-interacting. On this side, there are no correlations. And then, due to Cooper instability, there should already be something happening here, and you can actually see that here. If the interactions are really strong, you see these correlations even inside the Fermi sphere, which basically just means that the Fermi sphere disappears. Now, right, so this is a typical picture. Fermions pair up, they form a macroscopic condensate, or macroscopic in this case, it's only a few particles, but it is something that you can measure when you measure the pair correlations all at the same time. Now, odd frequency superconductors are the case where this would not work. Right? So what the heck is odd frequency superfluidity? It cannot be detected by such an experiment because these pair correlations would actually vanish at equal time. And the idea is that there are pair correlations if you take measurements at different times. Right, so this goes back to some idea that Berezinski had in the 1970s, so where the average many-time wave function of the pairs would depend in an odd manner on the time difference between the temporal arguments. Now, he tried to explain superfluid helium-3 with it, which was a sort of unsolved problem at that time. Turned out that this did not explain the superfluidity of helium-3. However, it has now about 450 citations, this paper. It's become a fairly big topic. Some of you may actually know more about it than I do. I just learned about this fairly recently. There's no literature related to ultra-cold atoms for some reason. And everybody is using these anomalous Green's function here, for which you need to forego particle number conservation to make sense out of that, right? So this was sort of my motivation for getting into this. So it gives you a way to classify symmetries of Cooper pairs. So the usual ones that we have for BCS theory, they would be, singlet pairs with, even symmetry in momentum. So S wave or D wave, singlet pairs, and if you have a triplet, you would need to have then odd symmetry in momentum or space. Now, the idea is that if you have this odd frequency pairing, or Berezinski pairing, you would have an odd frequency and an odd symmetry in either time or frequency that is equivalent, which would allow you to have a singlet then with a p-wave Cooper pair, for example, right? Or a triplet with an X. Yeah. So there are two possible modes of these odd frequency correlations. So the first type would be, in principle, very interesting. So there is no conventional Cooper pairing, it's only odd frequency. Now this has never been seen in experiments. There are models. So one of the first ones here, series model, would be one by Abrahams and Balatsky from the 1990s, but there are many questions, there's no experimental evidence, and in fact there are some serious questions on the theory side, because there's predictions that Meissner effect would actually work in reverse. It would, these states would attract magnetic fields, and then the question is, could that be stable in the first place? Right. The other one, which is a little bit less speculative, is that odd frequency correlations coexist with conventional even frequency correlations, even frequency superconductivity. An example would be here, and that is from an actual experimental paper, where you have a conventional superconductor, let's say niobium. You have an interface that is ferromagnetic, and then in principle, these conventional Cooper pairs, they can't penetrate into this ferromagnetic regime. But according to theory, they would be converted into odd frequency pairs, which then can be detected here. So they give some kind of long-range proximity effect of tunneling of Cooper pairs into regions where otherwise they wouldn't be found. So there's quite a bit of theory, of literature on this. People believe that that is actually true, and that this is what is happening. And this is sort of the state of the field there. So when we started thinking about this problem, we wanted to see, could we, maybe in logical atoms, could you generate something like that? Are there models that you can think of that experimentalists could realize, for example? But the first stumbling block, and this is maybe also due to my education, I was educated in part by theoretical chemists who have always a finite number of electrons. I don't like these anomalous averages, right? Because if you assume that the particle number is conserved and is fixed, some particle number n, then this anomalous average will always be zero, right? So in order to make sense of this, you would need superpositions of states that are in superposition between different particle numbers. So Phil Anderson was very much promoting this idea that you have some spontaneous symmetry breaking that leads to the state of superposition states. And Tony Leggett, I think originally also worked in this matter, and then later said, okay, but hang on, maybe we should take number conservation seriously, right? So why? First of all, the model Hamiltonians that we have, and probably in real life as well, have two particle interactions, they actually conserve particle number, right? The next question is, which is maybe a little bit more controversial, but I think most people believe that superposition states with different particle numbers don't actually exist in nature because they violate a superselection rule.
Sorry, the ground states that you used here is the coherent state.
So yes, people exactly. In order to make sense out of this, in order to be able to write this and not have it being zero, you would need a coherent state. But for a coherent state, you need a coherent state is in superposition with different particle numbers.
Yes.
Right? Now, electrons are massive particles, and at least when I learned about quantum mechanics, the book says there is a superselection rule that doesn't allow you actually in nature to make a superposition of states with different number of particles.
Yes.
And most people seem to believe that that is true. And as long as your Hamiltonians, your mechanisms don't allow you to coherently destroy particles, there's no way to get there when you start with a fixed particle, right? The best you can have is you can have states that are mixtures of different particle number. But if you take an average here of a mixed state with different particle number, you still get zero. Right? You actually need a coherent state in order to have this non-zero. Right? So, and Leggett made the point that, yes, it is working with coherent states is very convenient, and you can do many calculations fairly easily when you start with coherent states. However, maybe it is still worth checking whether you get the same results if you use a theory that avoids the coherent states. So he wrote a book, Quantum Liquids, where he gave an example of how to formulate BCS theory, for example, without relying on coherent states and enormous averages, and he showed that could be done. But nobody has done that for these odd frequency superfluid states. So this is basically what we did. Right. So other examples are, exactly solvable models that are beta-ansatz solvable. Richardson pairing model, for example, work in a fixed particle number sector. Right. So if you're in a fixed particle number sector, again, you naively calculate that correlation function will just be zero. You don't get an answer. And numerical techniques like our Monte Carlo, for example, work in fixed particle number sectors as well. Right. So how do you do this theory if you want to avoid coherent states? So you can define, work with Penrose-Onsager and Yang, or off-diagonal long-range order row is another jargon term that's sometimes used. So the idea is you start with a correlation function that is well defined and is non-zero. For bosons, you would look at the single particle density matrix. You find that it has nice properties. It's Hermitian or symmetric and positive semi-definite. So it has a spectral representation where you can write it in terms of its eigenstates and its eigenvalues. They're all non-negative and they sum up to the particle number. And then you define that you have both condensation if one of these eigenvalues is actually large and comparable or actually proportional to the particle number. And we define that as a criteria for when you have Bose-Einstein condensation. Strictly to do it, you need the thermodynamic limit and that ratio n0 over n larger than 0. Yeah. So Yang generalized that in the 1960s. He generalized that to fermions, where you need to look. So in the one-body density matrix, you can't get this for fermions because otherwise you would have a Bose-Einstein condensate. For fermions, you need pairs, so you need to look at the two-particle density matrix, and spectral representation can be written like this. So again, you would have a fermion pair condensate if one of these eigenvalues is larger than one. Is large and scales with the total number of particles. So what we did is we generalized this to a time-dependent two-body correlation function. which is a little bit unconventional in the sense that mostly people write this with time ordering operators, and we have to distribute the time arguments in a slightly unconventional way. But if we do that, we get the nice properties. Yeah, this is Hermitian, it's positive semi-definite, has a constant trace. And the interesting thing also, it's completely anti-symmetric with under exchange of the indices k and l and I and j only at constant time. Right, so because of these properties, we can write spectral representation, and that allows us to define condensation of time-dependent Cooper pairs when this N0 is greater than, is large, is macroscopic.
In this case, you need also long-range order, like the distance of the itinerant and it's far from each other.
Yes, this is the same as off-diagonal long-range order. Right, and this is just a slight generalization of what C and Yang did for fermions in saying that we have put these different time arguments in there. Right, so now assuming that you have one single macroscopic eigenvalue and approximately this correlation function now factorizes, you can define this as an order parameter, as a superfluid order parameter, and then you can look at its properties, and specifically we look at the version that is symmetric under exchange of I and j and the one that is antisymmetric under exchange over I and j. So the one that is antisymmetric, that will be your conventional even frequency superfluid order parameter, whereas this one that is symmetric under exchange will have to be odd in time, and that would allow you to define actually what is this odd frequency induced order parameter. And again, I explained earlier that there are two different ways of getting to this. We see this in this formalism as well. So there's one that we call transformed symmetric order. So if there is an antisymmetric part, so for example, at t equals 0, the whole thing does not disappear, is not 0, then you can actually show fairly easily that the symmetric part here can be written as a product of a matrix, which I think I did not define here, but it's a correlation function. So it's proportional to this antisymmetric order. It's proportional to t as well. So that makes it odd frequency.
The symmetric part means like anti-symmetric at the time, because you want to have the time ordering. After that, you need to satisfy the anti-computation of the fermion, right?
So first of all, as soon as you have the canonic anti-commutation relations for fermions only apply at equal time, right? And if the time is not equal, you actually don't know. It really depends on the dynamics of the system.
But my point is that phi s here is the symmetry part. It's odd on the time, because when you do the time ordering will make it work.
We deliberately do not do time ordering, because the time ordering screws it up, everything. Yeah, so there's a tricky part about time ordering, because that is what conventionally is being used. But probably the reason that...
So the point is that the two fermions at like at different time, you can do like anti-commute with them, and then if it's far from each other, it needs to be anti-symmetry.
So if you start out with this thing, then you can show under the time ordering that exchange of I and j is equivalent to exchanging T1 and T2.
Right.
Right. So this makes even odd frequency the same as being symmetric under exchange
So
I and j.
point that
Yes.
your phi have the same, like similar logic over there.
Right, in this paper about which I'm talking here, we didn't do this. We found later an extension to put time ordering in there, actually to have a similar property. Yeah, but the way we defined it here, you see there is no time ordering here. You can add a second term and have something that is not exactly time ordered. It's not the conventional time ordering, but it's an alternative time ordering, which gives it a similar property. So that in fact, this one is strictly, then the equivalent one would be strictly odd in time, and this one would be strictly even in time. So here it's not actually guaranteed in this formalism. And then, of course, the interesting part is whether you can have this what we call generated symmetric order, where when t equals 0, actually this whole thing vanishes, or at least there is no macroscopic part there's no macroscopic factorizing part of this two-body correlation matrix. And then the eigenvalue, the largest eigenvalue itself is a function of time, so it would be quadratic in time. So that that is still possible. Right. So what we're doing here is really just, we're developing formalism and then seeing what are the mathematical possibilities there. So in that sense, it's yeah. Okay. I realize I've gone over time, so I don't want to spend too much on this one, but maybe it's still interesting to tell you that there's the Meissner effect, which is that a magnetic field is not compatible with having a superfluid order parameter, a superconducting order parameter. It follows directly from offline long-range order, right, as I've defined it before. And this was actually only realized, in the 1990s by George Sewell. He proved that for the first time. And the nice thing that we found is that this time-dependent formalism that I just explained to you can be easily extended. So if we have a macroscopic time-dependent pair condensate, it follows that the magnetic field vanishes. So this proves that if you have an odd frequency superconductor, it's a real superconductor in some sense, right? It's not consistent with the magnetic field. Right, and the rest maybe I'll go over this. I'll skip essentially. So we've looked at some candidate systems. We have an idea on how to realize something in ultra-cold atoms. It's the transformed symmetric, what we call transformed symmetric order. So in some sense, it's one that already is a conventional fermionic pair condensate, but you get spin triplet pair correlations if you do the measurement of pairs in a time-delayed way. Right, so I told you before that if you do the measurement if you measure all of the atoms in there at equal time, you only find the usual even frequency pair correlation. So you have to do a different measurement. And in the particular case where there's a Zeeman spin splitting between the atoms, between spin up and spin down atoms, you can actually find those as well. Yeah, so I think I will leave you with that. I think there are plenty of opportunities to do work with ultra-cold atoms. This is what motivates us. There's some work to do, obviously, in this area, which we haven't yet done. But we're working on this. Yeah, and maybe with this, I will leave you with this. With the 3 publications that I talked about, and in the background, Sergey gets a point if he tells us where the background picture was taken.
I guess this is, what was the name of this house volcano there? And then, well, I forgot.
It's called Rangitoto.
Angetoto, yes. Okay. Okay, thank you, Joachim. And as before, we had already many questions, but still, if there are some urgent questions right now. Yes, Alex.
Just very much. Last one. The next one, sorry. Yeah,
This one?
The simple solvable models. According to the
Exactly, solvable models, yes.
Yeah.
And
You give examples.
examples of exactly solvable models. Well, one thing that we're currently looking into is the fermionic Tongschnur-Doe gas, which is a model of basically point-like P-wave interactions between fermions that maps to a non-interacting Bose gas. So we're currently working on this. So we think so. It is a conventional P-wave superfluid, and what you can already see easily is that it's a purely even frequency superconductor if you have a homogeneous system. But as soon as you introduce boundaries, you get some odd frequency correlations induced near the boundaries. Right? Or I mean, there could be other exactly solvable models that one would look into. So this is more like look out for the future.
Okay, more questions? If not, then let's thank our speaker again. Again, both speakers